So yesterday we discussed about the little introduction about the PN junction formation. Okay, once again I will revise this. Okay, then after that we will go for the forward. What is the forward bias and reverse bias? Okay, so first of all, so one more time we are discussing about the formation of PN junction diode, how it will be formed. Okay, so let us take by using metallurgical methods, so we can form the PN junction diode. In that metallurgical methods, so there are so many ways will be there. So one way is, so while preparing the material, while preparing the semiconducting material, so what they will do means at higher temperatures, so one side they will dope with pentavalent atom, another side they will dope with a trivalent atom. So at that situation what happen means, so PN junction will be formed. PN junction will be formed. Otherwise, one more is, so one P type material and N type material is, so contact, that means contact with closer with each other. If you will heat to the higher temperature, what happen, that PN junction will be formed. PN junction will be formed. Okay, simply, so just what is that here, PN junction is formed by joining the P type and N type semiconducting material. Okay, see here. So what happened if you join the P type and N type semiconducting material? How junction will be formed? So in case of N type material, what are the majority charge carriers? Electrons. In case of P type, majority charge carriers are the holes. Okay, so like in that, suppose if you will take any gas, suppose if you leave the gas, what happen, it will diffuse from one place to another place. That means higher density to lower density, higher density to lower density. Similarly, in that material also, these electrons will diffuse from higher dense place to lower dense. Okay, here in case of N type, N region, so what are the majority charge carriers and high dense carriers? Electrons. Okay, so here electrons are high dense. Okay, that's why, so these try to diffuse, these electron try to diffuse to the P region. Okay, similarly, in P region, what are the majority charge carriers means? Holes. Here density of the holes is high. So these try to diffuse from, so this region to this region. Okay. So this is initial process. This is initial process. Okay. So now, so while diffusing what happened we will discuss. Okay, now electron is diffused from here to here, here to here. So what happened, so electron is diffusing means here electron is leaving means, so one vacant will be present. Okay, that is opposite ion vacant. Okay, suppose electron have negative charge, so what, which vacancy will be present means positive ion vacant will be present in the crystal site. Positive ion site vacant will be present if electron will be, so diffuse from here to here. So what happened, so here positive ion vacant will be present, positive ion vacant will be present in the crystal site. So that positive ion vacant will be, does not move from one place to another place, does not move from one place to another place. So similarly, so whatever the surrounding electrons will be there, so those electrons will be diffused from here to here. So at that places what happen, all positive ions will be, all positive ion core will be present, positive ion core will be present here. Okay, similarly, so in this side, so these holes are recombined with these electrons. So whatever the nearer holes will be there, so those holes will be recombined with these electrons. So because of this recombination process, what happened here, negative ion core will be developed in this region, negative ion core will be developed in this region. So because of this positive ion core and negative ion core, what happened, some potential will be developed, some electric field will be developed here. So because of this positive, so positive ion core will be developed on N region. Similarly, negative ion core will be developed on P region. So because of the these positive and negative ion cores, what happened here, some electric field will be generated. Electric field will be generated. Due to that electric field, so some potential difference or voltage. So voltage will be developed.
సేమ్ మధ్యాహ్నం
Who is that? Who is that?
అదే 11:30 ఒంటి గంట
Who is that?
మెల్ల బయటకు వస్తాం
D4. D4. Why are you talking? Okay, you don't have common sense. Okay, so now here, see, so here positive ion core will be developed on N region and negative ion core will be developed on P region. Okay, because of these positive and negative ion cores, some electric field will be developed. Some electric field will be developed here. So due to that electric field, some potential will be developed. So that potential region we will call it as space charge region. That potential region we will call it as space charge region. Okay, see here. One more time I will repeat here. Since N type region has high concentration, high concentration of electrons, okay, and P type have high concentration of holes. Electron diffuse from N type material to P type material. Similarly, holes move from holes diffuse from P type material to N type material. Okay, so if the electrons and holes were not charged, so this diffusion process would be continue the same as two gases come into contact with each other. So this diffusion process will be like two gases come contact with each other. Okay, now see here. However, in PN junction, when the electrons and holes move to the other side of the junction, they leave behind exposed charges on the dopant atoms, so which are fixed in the crystal lattice and are unable to move. Okay, so that means already we discussed here. So while moving the electrons here, what happened? Opposite charges will be developed. Okay, so that opposite charge we will call it as positive ion core. Positive ion cores. Okay, so positive ion core is exposed here. Similarly, negative ion core is exposed here. Okay, and so due to that ion core, what happened? Electric field will be developed. Okay, so this region called, so also we will call it as depulsion region. Depulsion region. Okay, the electric field quickly sweeps the free carriers out. Hence, the region is depleted of free carriers. So that means, so here electric field will be produced due to the these ion cores. So that electric field send out the whatever the free carriers will be there. Okay, whatever the free carriers will be there inside this region, so that electric field send out those carriers. Okay, and this region will be, this depulsion region or space charge region will become charge free. That means carrier free. There is no free charge carriers inside the depulsion region. Okay, so due to that electric field, some potential difference will be developed. That is the VB. Okay, for potential difference will be formed at the junction. So that is the VB. Okay, this is about the how depulsion layer will be formed. How depulsion layer will be formed. Okay, that is the reason for, so here junction, this is called as junction also. Okay, so in between P region and N region, so there is some depulsion layer will be there. So due to that depulsion layer, what happened? So there is no flow of electrons or holes after certain time. Okay, initially either electrons or holes diffuse from one region to their concentration difference, concentration gradient. That means high concentration to low concentration, they will diffuse at initial time. After certain time, so in between one junction will be formed. Okay, so that junction we will also call it as depulsion region, space charge region. Okay, so this is the PN junction. In between the P type and N type material, junction will be formed. That's why this is also called as PN junction. Okay, so this total combination we will call it as PN junction diode. Okay, now schematic diagram of the PN junction diode. Schematic diagram of the PN junction diode here. So this positive region. So positive region means so P type region. So we can represent like this. P type region we can represent like this, and N type region we can represent like this. So this P type region we will call it as anode, and N type region we will call it as N region, and simply N region we will call it as cathode. cathode. Okay, so how to remember this means already cathode is pronounced like a K, it starts like a K, so that's why. So this symbol is opposite of the K, that means yeah, so that's why, so we can call it as cathode. Just simply remember how it will be. Cathode means just it reflect like a K, it reflects like a K. Okay, that's why, so we simply call it as this is cathode and this is anode. Okay, this is anode. P region is called as, P region is nothing but positive holes will be present, so that is that will act as a cathode. N region, so number of charge carriers are electrons in N region. Okay, that's why this is negative and it represented as a cathode. Okay, now coming to the energy diagram of PN junction diode. Okay, so before the formation of PN junction, the Fermi level lies to the valency band in P-type material and nearer to the conduction band in N-type material. Okay, if you observe it, this is the P-type material. So before formation of PN junction, so if you will take the P-type material, that Fermi level will be nearer to the valency band. Fermi level will be nearer to the valency band. Similarly, if you will take the N-type material, that Fermi level will be nearer to the conduction band. Fermi level will be nearer to the conduction band. This is before formation of PN junction diode. PN junction. Okay. Now, so when P-type material is brought closer to the N-type material, a contact potential VB is developed, which is due to the potential of depletion region on N side, P side respectively. Okay, so due to the, so if you bring P-type N-type material together, what happened? Depletion layer will be formed. So P-type, N side, so positive ion core will be developed. Similarly, in P region, negative ion core will be developed. This is because of this. So that means this is so due to the this positive ion core, some potential will be there. So due to the negative ion core, some potential will be there. See here. Yeah. So the constant or barrier potential due to N-type is Vn. Okay, due to these N-type charge carriers, some potential will be there. That is the, so Vn. Okay, so Vn, that potential, and P-type. So due to P-type charge carriers, some potential will be developed here. So that is, so Vp. So potential due to the uh, P-type charge carriers. So Vn means potential due to the N-type charge carriers. Okay, so therefore, so resultant potential difference VB is equal to Vn minus Vp. Okay, so that is about the resultant potential difference. Now, resultant electric field. So what is the electric field? So that means energy difference. Similarly, so that energy difference we will call it as electric field here. Okay, suppose this is the conduction band energy in P region. Similarly, this is the valence band energy of the P region. Okay, if you will take so that electric field will be, so valency band of P region minus, so valency band of N region. Okay, so this is the valency band of N region, so this one, and valency band of P region. Okay, so energy difference between these two, so EVP minus En, so that is called as, so this difference, so energy difference between these two, okay, is called as electric field. Electric field developed due to the PN junction. Electric field developed due to the PN junction. So this is equal to the this. So here, so what is that energy of the conduction band of P level minus energy of the conduction band in N level. So this energy level minus this energy level. So difference between these two energy levels gives the electric field. Okay, so these two are the same. Okay, so difference between this, and similarly difference between this and this. Okay, so those two are the same. That will gives the, what is that, electric field. So there is a relation between electric field and potential, that equal to, so E is equal to small e into capital V. Okay, so this is VB is the, what is that, potential difference between the, so P region and N region. So now electric field due to the P region and N region equal to E into VB. Okay, after junction formation, the Fermi level will becomes common for both types. common for both sides. See here. So after junction formation, what happened? So that Fermi level will become so common. So before that, how it will be Fermi level? So Fermi level. So before junction formation, Fermi level is nearer to the P region, and so this Fermi level will be here, and this Fermi level will be nearer to the conduction band. So after junction formation, similarly that Fermi level will be so nearer to the conduction band here also. Similarly, that Fermi level will be nearer to the valence band here also. But so that Fermi level is common for both P region and N region. So this is at equilibrium position. This is at equilibrium position or zero bias condition. Zero bias condition. Zero bias means without applying any external voltage. Without applying any external voltage, what happened? This will be that PN junction will be at equilibrium position. Equilibrium position. Equilibrium position is nothing but there is no flow of charge carriers inside the PN junction. Okay. So it initially already we said that initially there is a flow will be there. So after forming the junction in between the p-type and semiconductor, so p-type and n-type, so what happened? So there is no flow of either electrons or holes. So that condition we will call it as equilibrium position. So equilibrium position, that means without, that is equilibrium position occur so without applying any external voltage. So equilibrium position occur in PN junction diode. PN junction diode. Okay. So this is about the what is that electric field and potential difference in case of PN junction diode. Now coming to the so biasing. So there are three types of biasing. Three types of biasings are there. So one is the first one is zero biasing. Second one is forward bias. So third one is reverse bias. Okay. So zero bias, forward bias, and reverse bias. Okay. So we'll discuss about the these three types of biases. First one, zero bias. When diode is said to be zero biased, when diode is said to be zero biased, no external voltage is applied to the PN junction. Okay. See here. So if you will, so here this is the PN junction. So we are not applying any external voltage. So this situation, in this situation, so diode is act as so there is no conduction of electrons or holes. Okay. So that's why, so this condition we will call it as zero bias condition. Zero bias condition without applying any external field. So external field, there is no flow of current inside the this diode, inside the diode. This condition we will call it as zero bias. In this zero bias, already we discussed, at the zero bias this will be in equilibrium position. That's why Fermi level will be same for both N region and P region. N region and P region. Okay. So this is about the zero bias. Now, so energy level diagram here. Okay. This difference. So this difference gives the electric field. Already I said that. Okay. So this difference, energy difference between the, so these levels will give the what is that electric field. Okay. Now coming to the forward bias. Forward bias. So when positive terminal of the battery, so forward bias is nothing but, so what happened? So this is the so P region and this is the N region we are taking here. N region we are taking here. So this P region is connected to the positive terminal of the battery. Positive terminal of the battery. Similarly, N region is connected to the negative terminal of the battery. Negative terminal of the battery. So if you connect the positive terminal of the battery to the P region, what happens? So P region is positive charge and holes. So in case of P region, what are the majority charge carriers? Holes are the majority charge carriers. Due to this positive terminal of positive terminal, what happened? These holes, majority charge carriers are holes here. These holes repelled by the this positive terminal. These holes repelled by the this positive terminal. Similarly, here electrons having negative charge. Electrons having negative charge and negative terminal is connected to the this N region. Okay. So that's why what happened, due to this negative charge, these electrons try to repel and so come closer to the this side, holes comes closer to the this side. Okay. So this situation we will call it as, this condition we will call it as forward bias. This condition we will call it as forward bias. In case of forward bias, what happen means, so this width of the depulsion layer will be decreases. Okay, see here. So that electric field also decrease. So electric field means this gap between, so this, that means difference between the this level and this level. So that also decreases. If you observe the energy level diagram, okay, so this is the energy level of the P region, okay, conduction band energy level of the P region, and this is the conduction band energy level of the N region. So difference between these two is, so will become reduced. Okay, now so this is the Fermi level is closer to the here conduction band, and in case of p-type region, so Fermi level is closer to the n what is that, valency band. Okay, now so these electrons, so electrons freely move from, so this conduction band to this conduction band. So due to this, so if it will be in forward bias, what happen, so here majority, in case of n-type region, what are the majority charge carriers? Majority charge carriers, electrons. Okay, those electrons are freely moved from this conduction band to this conduction band. Similarly, holes are freely moved from, so this valency band to this valency band. Okay, so if you observe here, so here recombination will be takes place at the junction. Okay, so recombination will be takes place at the junction. We will discuss that recombination, okay, so later in that application third unit. Okay, so there are some applications will be there based on this recombination. Okay, so in that forward bias, what happened means here, so there are majority charge in conduction band, majority charge carriers are electrons. So if it will be connected in forward bias, what happen, those electron will diffuse from this conduction band to this conduction band. Okay, p-type conduction band. That's why it act as a like a conductor. It act as a like a conductor in forward bias. In forward bias. Okay, so what is the reason means, here width of the depulsion layer will be decreases. Width of the depulsion layer or space charge region will be decreases. Okay, so due to the decreasing of the space charge region, what happened, so these electrons will freely move from conduction band to this conduction band. So that's why what happened here, so what happened, so this will act as a conductor in forward bias. Diode will act as a conductor in forward bias. Okay, so this is about the forward bias. Next we are going to the reverse bias. Okay, to the n side, and negative terminal of the battery is connected to the p side. Okay, so then BN junction is known as reverse biased. Okay, see here. So positive terminal of the battery is connected to the negative terminal of the battery. Similarly, n region is connected to the positive terminal of the battery. So p region is connected to the negative terminal of the battery. Similarly, n region is connected to the positive terminal of the battery. In this situation, what happened? So these electrons are try to attract towards to the positive terminal. Try to attract towards to the positive terminal. Similarly, so these holes try to attract towards to the negative terminal. So that's why, so what happened, width of the depulsion layer will be increases. Width of the depulsion layer will be increases in case of reverse bias. So what happened in reverse bias means, so negative terminal of the battery is connected to the, so p region, and positive terminal of the battery is connected to the n region. So because of these connections, what happened, so those holes are try to attract towards to the negative terminal, electrons are try to attract towards to the positive terminal of the battery. So that's why width of the depulsion layer will be decreases. Width of the depulsion layer will be increases. Okay, so width of the depulsion layer will be increases means there is no conduction. There is no conduction of the majority charge carriers here. There is no conduction of majority charge carriers. Okay, now observe this. Okay, so this is the energy diagram of the reverse bias. Energy diagram of the PN junction diode in reverse bias. Okay, see here, this is the P region and this is the N region. So in P region, holes are, that means Fermi level of the holes will be nearer to the valence band. So here of Fermi level of the electrons will be nearer to the conduction band. Okay, so due to this, what is that, potential barrier. So these electrons does not move from, so this valency band to conduction band, because this barrier width is very high. Barrier width is very high. So that's why. So those electrons does not cross from so this barrier width. This barrier width. So that's why. So there is no conduction will be possible. There is no conduction will be possible in reverse bias. So that's why PN junction will diode. PN junction diode will act as a like a switch, like a switch. PN junction diode will act as a like a switch. In forward bias, it act as a conductor. In reverse bias, it act as a insulator. Insulator. That means if you switch on means so that is in forward bias. If you switch off means that is in reverse bias. So that's why so PN junction will act as a so like a switch. Okay. So in forward bias it act as a conductor, reverse bias it act as a insulator. So this is about the forward bias and reverse bias. Okay. So this is okay. Now coming to the IV characteristics of PN junction diode. IV characteristics of the PN junction diode. Okay.